Notice that if both sides of an equation can be expressed using the same base, like we have here, a to the u equals a to the v, then it follows that u equals v. We can simply drop the bases and set the exponents equal to each other and then solve. For example, let's solve 5 to the negative x equals 125. The left side is pretty simple. It's just 5 to the negative x. Let's see if we can rewrite 125 with the same base. And we can. 125 is 5 cubed. Notice that you have the same base on both sides of the equal sign. If you ever have the same base like this, we can simply remove the base, we can remove the 5, and set the exponents equal. Negative x equals 3. And then simply divide by negative 1, and we get that x is negative 3. In our second example, it's a little more complicated, but notice that we have different bases. We have 9, 27, and 3. But what if we can write them all as a power of the same base? And we can. 9 we can rewrite as 3 squared. So we have 3 squared raised to the 2x times 27 we can rewrite as 3 cubed. We have 3 cubed raised to the x squared. And then the right side is good. It's already 3 to a power. Now we want to go through and simplify this. Up first, we have 3 squared raised to the 2x. Power to a power, we multiply. So that is 3 to the 4x times, again, here we have power raised to a power. So the cubed raised to the x squared power, we're going to multiply. That is simply 3 to the 3x squared. And that is still equal to 3 to the negative 1. Now, a different exponent rule, we have bases that are being multiplied. Whenever you have bases that are the same base and we're multiplying the bases, we can add the exponents. So we have 3 to the 4x plus 3x squared equals 3 to the negative 1. Notice at this point we have 3 raised to a power equals 3 raised to a power. Whenever you have a single base on both sides of the equal sign and they are the same base, we can simply remove the base and set the exponents equal. So we have 4x plus 3x squared equals negative 1. Notice now we have a quadratic equation. So let's set that equal to 0 and solve. So I'll reorder that a little bit so that we have the x squared term first. And I'll add the 1 to the left side, thereby setting it equal to 0. Now we can use the AC method. 3 times 1 is 3. Two numbers that multiply to 3 and add to 4 are 3 and 1. So we can factor by grouping 3x squared plus 3x plus x plus 1 equals 0. Factor out the 3x. We're left with x plus 1. And then the right two only have 1 in common. Factor it out, you're left with x plus 1. Continuing to factor, we have x plus 1 times 3x plus 1, all equal to 0. Then set each of those factors equal to 0. And solving, we get x equals negative 1 and x equals negative 1/3. In our third example, we have lots of e's. The left side looks pretty simple, the e is by itself, But on the right side, notice we have two different factors. Let's use some exponent rules to make that a single e to a power. So we have e to the x squared equals e to the 3x times, we're going to use the property that allows us to push this e squared to the numerator. And that is done by making that -2. Making that exponent negative, we'll push it to the numerator. And now we have a base times a base, and it's the same base. When we're multiplying bases, we can add the exponents. So we have e to the x squared equals e to the 3x plus -2, or simply -2. Now notice the bases are the same. If the bases are the same, we can simply drop those bases and set the powers equal. X squared equals 3x minus 2. We're left with a quadratic, so we can set that quadratic equal to 0 by subtracting 3x and adding 2. And now we'll factor. Two numbers that multiply to 2 and add to -3 are -2 and -1. Set each of those factors equal to 0 and solve. We get x equals 2 and x equals 1. Now bear in mind that this trick that we're using where we drop the base, that doesn't always work. It only works when we have two bases that are the same base raised to a power. We'll see in future sections that that doesn't always work, because sometimes we might have +1 on the outside, or we may have 2 times something. There could be other factors that come into play, and we need logarithms. But for now, as long as the bases are the same and there's nothing else beside those bases, we can use this trick.